Hello friends, welcome to our YouTube channel. Today we are going to study Ramsey's theorem. Let's begin by a small introduction. Ramsey theory is the study of questions of the following type. Given a combinatorial structure, for example a graph or a subset of integers, how large does the structure have to be to guarantee the existence of some substructure with a given property? This theory has applications in the design of communication networks and other purely graph theoretical contexts, as well as interesting problems in elementary number theory. Definitions of the Ramsey's theorem. The basic definition can be given by for a fixed positive integers r and b, every sufficiently large party will contain a group of r mutual friends or a group of b mutual non-friends. Alternative definition of Ramsey's theorem is: let R belongs to N, then there exists an N belongs to N such that any two-colored complete graph Kn contains a monochromatic subgraph Kr of Kn. Ramsey numbers. So, to understand Ramsey number, we will consider this example. The problem statement is: show that any party with at least 6 people will contain a group of 3 mutual friends or a group of 3 mutual non-friends. Let's say we make a party with 6 members named A, B, C, D, E and F as shown in figure A. Let us consider A. Now A will have at least 3 friends or at least 3 non-friends. Without the laws of generality, we can safely assume that B, C and D are friends with A as illustrated in diagram B. A, B, C and D are friends with A. Now, if any pair of them are friends with each other, then that pair with A will form a group of 3 mutual friends. If no two of them are friends, then they are a group of 3 mutual non-friends as shown in diagram C. Here B, C and D are forming a group of 3 non-friends. Now, above problem can be rephrased in graph theory terminology in the following manner. The problem statement will be: show that a graph with 6 vertices will either contain a clique or an independent set of a set of 3 vertices, where a clique is a subset of vertices such that there exists an edge between any pair of vertices in that subset of vertices. This is equivalent to having a complete subgraph, and an independent set of a graph is a subset of vertices such that there exists no edge between any pair of vertices in that subset. Definition of Ramsey numbers. The Ramsey number Rm, n is the smallest party size that guarantees a group of m mutual friends or a group of n mutual non-friends. Alternatively, it is the minimum number of vertices a complete graph must have so that if every edge is colored blue or red, there is a red clique of m vertices or a blue clique of n vertices. R1, k is equals to Rk, 1 is equals to 1. The second property is R2, k is equals to Rk, 2 is equals to k. The next one is R of R, b is less than or equal to R of R minus 1, b plus R, b minus 1. Consider a complete graph 1, R of R minus 1, b plus R of R, b minus 1, vertices whose edges are colored with 2 colors. Pick a vertex V from the graph and partition the remaining vertices into 2 sets, M and N, such that for every vertex W, W is in M if V, W is blue and W is in N if V, W is red. Because the graph has R of R minus 1, b plus R of R, b minus 1 is equals to mod of N plus mod of N plus 1 vertices, it follows that either mod of M is greater than or equal to R of R minus 1, b or mod of N is greater than or equal to R of R, b minus 1. In the former case, if M has red complete graph of B vertices denoted by KB, then so does the original graph and we are finished. Otherwise, M has a blue complete graph of r minus 1 vertices, which is denoted by k of kr minus 1. And so, M union V has a blue complete graph of r vertices, which is denoted by kr by the definition of M. We can find lower and upper bounds in which Ramsey number can lie. For example, rk, k, we can prove following bound. 2 raised to the power k by 2 is less than r of k, k, and r of k, k is less than 4 raised to the power k. One trivial property of Ramsey numbers that follows easily from symmetry is r of r, b is equals to r of b, r. Now we will focus on application of Ramsey numbers, particularly in the information theory.
Let G is equals to V, E be a graph corresponding to an information channel, which is noisy, where V represents the input set, means all possible letters the channel can transmit in one use. In each channel use, a sender transmits an input and a receiver receives an output. The vertices corresponding to two letters are adjacent if and only if both can result in the same output. The maximum number of letters that can be transmitted in a single use without error is then the maximum size of an independent set, denoted by alpha G. To obtain larger unambiguous code alphabet, it is suggested to introduce noisy channels whose graph is the product of graphs. Let Gn denote the graph whose vertex set is Vn and two vertices u1, u2, u3 up to un and v1, v2, v3 up to vn are adjacent if and only if for all I from 1 to n, either ui is equals to vi or ui vi belongs to E. Alpha of Gn is the maximum number of messages that can be transmitted in n uses of the channel. There is a famous theorem related to this. If G and H are any graphs, then alpha of G into H is less than or equal to R of alpha of G plus 1, alpha of H plus 1 minus 1. This gives an upper bound on the size of an unambiguous code alphabet if the graph of the noisy channel is G2, and Gn can be used to get larger and larger unambiguous code alphabets, but with a cost to efficiency by using longer strings. To compensate, we consider the number alpha of Gn raised to the power 1 by n as a measure for the capacity of the channel with an unambiguous code of alphabet of strings of length n. The Shannon capacity is defined as C of G is equals to limit n tends to infinity alpha of Gn raised to the power 1 by n. It represents the number of distinct messages per use the channel can communicate with no error while used many times. If G and H are graphs of channels, then the union of the channels corresponds to the situation that either one can be used. It is also known quite famously that C of G plus H is greater than or equal to C of J plus C of H. And inequality holds if the vertex set of one of the graphs can be covered by alpha of G clicks. The largest number of bits a channel can communicate without error in a single use is gamma of 1 is equals to log of alpha of G. If a set I is independent in G, then I cross I cross I cross up to I is independent in Gn, and so alpha of Gn is greater than or equal to n times alpha of G. Gamma of n is equals to log of alpha of Gn is the largest number of bits the channel can communicate without confusion in n uses. Hence, gamma of n is greater than or equal to n times gamma of 1. N of L is equals to maximum of alpha of Gn or alpha of G less than or equal to L, and Rn of L is equals to R of K1, K2 up to Kl plus 1 minus 1. Here the edges are colored with n colors. Erdos even proved that Rho n of L is equals to Rn of L. This can be used to prove that 2 times gamma of 1 minus 1 is less than or equal to gamma of 2, and gamma of 2 is less than 2 times gamma of 1 plus 1. Now the C of n is equal to gamma of n divided by n, where n is the zero error n use capacity. Its limit C of infinity is also known as Shannon's zero error capacity. The highest per use number of bits the channel can transmit without error is known as Shannon's zero error capacity. C of infinity is greater than or equal to C of 2, and there are channels whose infinite use capacity is exponentially larger than their single use capacity. Dual source S consists of a finite set X and a set Y, and a support set S is subset of X cross Y. In a dual source instance, a sender is given an X belongs to set X and a receiver is given a Y belongs to set Y, such that X, Y is in the support set S. Now, the question is, what is the minimum number of bits the sender must transmit in the worst case in order for the receiver to learn X without error? The characteristic graph G of a dual source S has the vertex set X and X dash are the vertices which are belong to set X, are connected if there is a Y jointly possible with both, which means there is a Y belongs to set Y such that both X, Y belongs to S and X dash, Y belongs to S. The smallest number of possible messages the sender must transmit in the worst case for single instance of S is the chromatic number of G, X of G, and the smallest number of bit the sender must transmit in the worst case for a single instance of S is sigma of 1 is equals to log of G base X. In n instances of the dual sources, the sender knows x1, x2, x3 up to xn, while the receiver knows y1, y2, y3 up to yn, such that each xi, yi belongs to S, and the receiver wants to learn x1, x2, x3 up to xn. The number of bits the sender must transmit in the worst case for n instances of S without error is sigma of n is equals to log of gn base x. For every graph G of a dual source, sigma of 2 is less than or equals to 2 times of sigma of 1. Since if G can be colored with X colors, then G2 can be colored with X2 colors. For some dual sources, fewer bits are enough. A graph is called self-complementary if it is isomorphic to its complement. A graph is called Ramsey graph if both its independence number and clique number are polylogarithmic in the number of vertices. Let A be finite abelian group and a set K which is subset of A is symmetric if minus K is equals to K. The Cayley graph over A with respect to a symmetric set K has vertex set A and A, B belongs to A are connected if A minus B is in K. Allen and Orlinsky use probabilistic constructions of self-complementary Ramsey graphs that are also Cayley graphs to show that for every prime power V congruent 1 mod 4, there is a V vertex Cayley graph G with independence number at most 1 plus O of 1 into 16 log square V such that x of G is greater than V divided by 1 plus O of 1 into 16 log square V, while x of G2 is less than or equal to V. This implies that for arbitrarily high values of O of 1, there are dual sources where sigma of 2 is less than sigma of 1 plus 2 times log of sigma 1 plus 4 plus O of 1. These are sources where the number of bits required for a single instance is comparable to the size of the sources. But two instances require only a logarithmic number of additional bits. Okay, thanks for watching this video.